The voltage divider equation. Efficient, intuitive, easily applied, and quick to learn. Welcome to the lesson in which we look at how to solve for the voltage across specific components without resorting to any kind of current formula. First of all, look to this circuit on your left. It is familiar in this region here, except perhaps that it does not have a battery. Instead of a battery, I've simply written 10 volts here and 0 volts here. This is equivalent to saying that there is a battery here with no extra components of 10 volts. But we can skip that by just writing the voltage a charge starts with up here and the voltage it finishes with down here. Secondly, I've drawn a funny part of the circuit here sticking out. Don't be confused by this. All this part is here is an apparatus which allows us to measure the voltage over this component here. So if I were to put a voltmeter here, I would simply be measuring the amount of voltage dropped over this 4 kilo ohm resistor. First of all, let's figure out how many volts go across this 4 kilo ohm resistor using our old method, using Ohm's law. So the total resistance in this circuit here is equal to 5 kilo ohms, is equal to total resistance. The total voltage in this circuit is equal to 10 volts. So if V equals IR, that's Ohm's law, then 10 equals 5, I will leave I as the mystery, I times 5 times 10 to the 3. The 10 to the 3 being here to put it in ohms from kilo ohm. So RT is actually equal 5 times 10 to the 3 ohms. Therefore, I, the current, is equal to 10 divided by 5 times 10 to the 3. Which comes to 0.002 amps. So now let's figure out the amount of voltage across this component. V again equals IR. We know there's 0.002 amps flowing through here. So the voltage across here is equal to 0.002 times 4 times 10 to the 3, bringing it into ohms, which is equal to 8 volts. This is, as I said, the long way of doing it. Let's use the voltage divider equation up here to find the voltage across this component very quickly. We said the total resistance was equal to 5 kilo ohms, 1 plus 4. So the voltage out here, the voltage that we'll measure, is equal to the voltage being put into the circuit, which is equal to 10, multiplied by the resistance of the component we're looking at, which is 4 kilo ohms, or we'll just say 4 times 10 to the 3 ohms, divided by the total resistance, which is 5 times 10 to the 3. Cancelling down those 10 to the 3s, we get 40 over 5, 4 times 10 at the top there, which is equal to, again, 8 volts. So using this equation here, shown here with real values, we don't have to work out the current flowing through that circuit to figure out the voltage across that particular component. Let's look at another type of question involving this formula. Instead of knowing the resistance, instead now we know the input voltage, which we knew before. The input voltage this time is 4 volts. We want a V out down here. So the voltage across this particular component to be 3 volts. And this resistor here is not a resistor with constant resistance. It's a resistor whose resistance we can vary with a variable resistor there. So if I'm putting in 4 volts here and I'm getting out 0 volts here, it must mean that combined over these two components, we should have a total of 4 volts. 3 volts are here, so we expect 1 volt to go across this resistor here. The question is, what resistance do we need to set this resistor to in order to get 3 volts across here? Well, it's very easy. We just use this equation up here. V out is equal to 3 volts. 3 is equal to V in, that's 4, multiplied by the resistor of the component we're looking at. So V out here is over the 1 kilo ohm resistor. So 1 times 10 to the 3, divided by the total resistance, which is equal to, total resistance here is equal to this resistance plus this resistance. That's 1 times 10 to the 3 plus a mystery. We'll call that R. So 3 equals 4 times 1 times 10 to the 3 over 1 times 10 to the 3 plus R. We need to solve for this R here. And the way you can do that is to first of all bring this 4 over here. So divide both sides by 4. 3 on 4 equals 1 times 10 to the 3 over 1 times 10 to the 3 plus R. Then we get 4 on 3, flipping both sides, so putting both sides to the power of -1. 4 over 3 is equal to 1 times 10 to the 3 plus R over 1 times 10 to the 3. Splitting up this fraction here, so we have 4 on 3 equals 1 times 10 to the 3 over 1 times 10 to the 3, that's this side here, plus R over 1 times 10 to the 3. And that simplifies to 4 on 3 is equal to 1 plus R over 1 times 10 to the 3. Taking 1 from both sides, we have 1/3 is equal to R over 1 times 10 to the 3. And finally we get, multiplying both sides by 1 times 10 to the 3, 1 times 10 to the 3 over 3, which is equal to approximately 333 ohms, or 0.333 kilo ohms. That is the resistance we would have to set this resistor to in order to get 3 volts across this component down here. There was an easier way to do this question. It was to, first of all, stop saying that this was V out and start saying that this was V out there. Actually, no, that would have not really improved matters. Let's talk about this conceptually for a second. Now I'll just explore that. V out 1 is equal to 4 times R over R plus 1 times 10 to the 3. Now it's not much easier to solve. It's similar. So talking about this equation generally, what is it actually doing? First of all, recognize that this number here is always going to be less than 1. The resistance of a single component is going to be less than the resistance of the whole circuit. So this is a fraction less than 1. And what it's saying is that the voltage you get out over a single component is a fraction of the voltage that you put in. So if I have a simple circuit here with 3 ohms here, 1 ohm here, 8 volts coming in and 0 volts over here, the voltage that I get out over this particular resistor here, V out is equal to the voltage in multiplied by the ratio of the resistance of this component here, 3 ohms, divided by the total resistance 4. So since this component here is 3/4 of the total resistance of the circuit, it receives 3/4 of the voltage that we're putting in, which will come to 6 volts.